So yeah, thanks everybody for coming today. I'm Marty Kandes. I'm in HPC User Services Group, and so today we're going to be talking about getting started with batch jobs on HPC systems. And so I'm going to go ahead and turn off my video just because for bandwidth purposes, but share my screen. And okay. So hopefully the screen is coming through. Cindy, can you confirm?
Yes, I do see your shared screen.
Okay, great. Okay, so yeah, this is the talk for today. So thanks again for joining. I'll post, I don't know if Cindy posted this in the chat, but I'll put this in the chat again just in case. Let's see, where's the chat?
I gotcha.
Okay, yeah, there's a link to the documentation here. Oh, thank you, Cindy. This talk is a new talk that I haven't given myself before. I'm sort of teaching new HPC users how to use and interact with the batch job system. But in my role here, I deal with this type of question every day. So it's good to sort of try to write down and convey to you like what I think is the right way to do this. But this talk is gonna be a little bit different. I don't have any slides. I have this tutorial that I've started writing that I kind of want to start walking through. It's not complete, but this is kind of a new idea of mine to start writing down more sort of tutorial focused material that we can provide you as users on our systems, like exercises that you can execute reliably and learn different concepts about on our systems if you're sort of new to HPC and are sort of intimidated by some of the things that you might be doing on the system. And so this is one of those efforts. It's not done yet, but I think it'll give you some, if you're new to working with batch jobs on HPC systems, hopefully it'll give you some context to what the batch job scheduler is, how to write these batch jobs correctly and sort of organize your and structure your workflows on these systems. Now, just a disclaimer. So I, as you can probably see from the screen, I work on a Linux system myself. All HPC systems pretty much run on Linux or some sort of Unix-like environments. So all of the tutorial material here is sort of assuming you have access to a Unix-like operating system environment. So if you're on a Linux machine or a Mac OS, you definitely have that. If you're on, say, a Windows system, you actually do have access to that kind of environment and the Windows subsystem for Linux. If you don't know what that is, I have a link here in the beginning of the tutorial to point you to some instructions that you can later go back to and install that on your Windows system and get. If you're not familiar with Linux, it's a good way to have an environment on your local laptop or desktop to learn some of these commands and how to interact in not only on in a Linux environment in general, but on HPC systems, right? Because that's generally what you're going to be doing as an HPC user if you're directly logging into the system, okay? Okay, so this is the structure of the talk. How I'm sort of structuring these tutorials is I kind of always want to start with in a place where we can all get on the same page and have the same understanding of some of the core concepts. And that's sort of this first section about managing Linux processes, right? Because that's ultimately what you're doing on an HPC system too with the batch job scheduler. And then in the second section, we'll talk about how batch jobs fit into managing your processes on an HPC system. And then we'll talk about some more advanced topics as we start talking about writing batch job scripts and submitting to the scheduler. And so I'm not exactly sure how long this is going to take. Again, this is my first time going through some of this material and it's not done yet. So if there are questions, please drop them in the chats. I definitely would like as many questions as possible as they come up, because I'm not sure exactly all the material yet that I would like to cover in this kind of talk in the future. So, okay, so let's go ahead and get started. So this is going to start in a very simple way. And this is sort of how I got started when I was a PhD student running my simulation codes for my research that I was doing in grad school, right? And it really started with manually managing Linux processes on workstation computers at the lab that we had, right? And so if there's a lot of terminology, especially if you're a new HPC user, you're not like a programmer by training, around Linux, all sort of all the computer science sort of jargon and HPC jargon that we're going to rely on to discuss sort of the concepts today, right? And so the fundamental thing that you need to understand is what a process is. So when we talk about a process in Linux or running on say an HPC system, we're talking about an instance of a computer program, right? That's being executed on the CPUs that you have available to you, right? So if you have a program that you're running, right, it's got some set of instructions that you want to run. That's written in some programming language. That's what's shown in this diagram is those instructions are stored in a file on a disk, in the physical medium somewhere. And when we talk about a process, that's actually the instantiation, the execution of that program on your computer system that you're running, right? And now there's a whole other things. We don't need to really talk about threads right now, but those are sort of subsets of instructions that are running inside these processes that can be sort of divvied up by the operating system to run on your CPU. But this is the fundamental thing that we're managing, both in this case, in this first section, we're going to manage processes manually. And then the whole idea about batch job schedulers and writing your batch jobs is having this scheduling system on the HPC system manage your processes for you. All right. Okay. So the example program that we're going to run is in this is very straightforward calculation of sort of estimating pi with a Monte Carlo. So I just wanted to have sort of a sciencey math program to run that we can utilize some computational resources and should be relatively easy to understand. This example is used a few different places. One of the good HPC tutorials from Lawrence Livermore Lab has something similar. This is actually their diagram. And what the program does is it's going to basically compute pi from randomly pulling numbers in a box. If it's in the circle, you count it, you do the counts of where the points in the area fall that are inside the circle versus ones that are outside, and that ratio of those counts of points give you an estimate of pi. So it's just a fun little algorithm that you can run and code up pretty easily. And there's a repository that we have with that code. Okay, or that I have with this code here. Over here, I have a terminal open on a system that's running Linux. It's actually a Ubuntu system, and it's running, if you're familiar with the Access CI resources, it's actually running on Jetstream, which is a cloud computing platform that you can get time on. And what I'm going to do is use this system here, which is allocated with sort of 2 CPUs to run these manual instances of this 4Pi program. Okay, so what I'm going to do is download the, oops. It's a little, clone this repository. Oh, it's already here. Clone the repository to my instance here. And so the idea of the tutorial, it'll give you some commands that you can run, and it'll show you what the expected sort of output is to sort of guide you through the material later if you come back to it. So we have a copy of the repository here. Right, you can sort of navigate around into the repo. There's 4 different versions of the program. There's one that's written in just straight a bash shell script. There's one written in C, 2 actually written in Fortran. And then another written in Python. And the Python one is the one we're going to start with for these exercises. Okay. And so I'm going to navigate to the Python directory. And the nice thing about the Python one is it's pretty simple program. It only takes one input, right? It just takes the number of samples that you're going to, run over this sort of, box simulation and count the ones that fall in the circle and the ones that fall outside the circle to get your estimate of pi. Okay. So all I want to do is run that program and see what the output is. Okay. That's what it does. You take the Python 3 command. That's just what you would run to run the Python on the system, the name of the actual program, and then it just expecting a positional argument of the number of samples here, right? And so that's kind of output you would expect. What I like to do when I'm running any sort of code usually is also measure the runtime of the system. Okay. So one convenient way to do that is with the time command, and the -p is just an option that allows you to format it, the output in a sort of portable fashion. Basically, it's just the number of seconds essentially for these 3 variables of runtime that are being used. If you're not familiar with the time command, there's these 3 different statistics about the runtime of your program as you run it, right? The real time is just usually what you care about, the real wall clock time, like how long did it take to run the application or the program. And in this case, it was, just half a second or so, a little bit more. The user is how much time your user process took. So that's basically it. And then sometimes if there's hangups with or time spent by the operating system with respect to running your process, your program, there'll be this sys time as well. Okay, it's not too important, but the real time is kind of what you usually care about when you're running an application, like how long did it take to run, right? And so we can increase the number of samples here, right? And it'll run longer, right? Because it's going to take more time to run the application for a larger number of samples, right? So if I go up, it just will keep running. And, with more samples in this case, you get a higher accuracy calculation for your estimate of pi. Now, when we talk about managing processes, there's really 2 types of processes, right, that you can have in a system, right? You have what are called foreground processes and background processes, right? And what's happening here, what I'm running here, right, in this terminal is a foreground process, right? It's actually running right now. I can't really do anything on my terminal while that process is running, right? Because it's running my pi calculation program, and it's a foreground process. It's interactive. It's what we would sometimes call also an interactive process, where I'm giving user input to the program, and through this terminal application, right? And I only gain back, as you saw here, the control of the terminal to run new commands after that process is run, right? And so that's a foreground process, right? And so let me run that again. I'm going to open up a second window here, right? And there's a command, if you're not familiar with, called top, that allows you to view the processes that are running on a system, right? So what we see here is I have my foreground process, this Python 3, pied up high with, I think it's 100 million samples here. You can see it running in this top program, right? This process is using 100% of one of the CPUs essentially, right? And this top command gives you a bunch of information about the processes or programs that are running on the system, right? You have an ID associated with the process, you have the username that's running it, you have what's known as the sort of the priority or niceness of the process assigned to the process. These other parameters have to do with memory, and how long the process has been running, right? So this top command is very useful for if you're just getting started on a system to sort of see your process is running, see how much memory or CPU might be utilized by the given program that you're running, right? So in this case, it's using a lot of CPU, but wasn't really using a lot of memory on this system. Right? Okay. So in contrast, you have other processes on the system that will run as what we call background processes, right? And these are some of the other things that you might see in the top program here, right? So like this system D here, this is a background process that's running, right? So this is part of the operating system that's running. A lot of these are running as the root user that's associated with your Linux operating system here. And these are running in what we call the background, right? They're running because the computer's on, essentially, right? It's running these system processes that keep your operating system chugging away, doing the things it needs to do, waiting for response, from your user input to say starting your shell or open this application, right? These are things that are sort of happening behind the scenes, always on the system, right? So one of the words that you might learn about these types of processes, they're also especially when they're always on, if a background process is always on, sort of waiting around in the background, these are what we call daemons usually, right? And so you can think about if I run top with the user command, or with the top with the user environment variable, just my username. You can see all the processes that my user is running. We might see here the SSHD daemon, right? That's because I've logged into this system remotely. So you'll see these background processes running in the top command as well. Now, let's see. Okay, yeah. Okay, so there's these two types of processes, foreground and background processes. And when you get started working on the command line in a terminal like this, you'll encounter both, right? And so one thing, right, obviously that you can do with the foreground processes, how do you terminate a foreground processes, right? Because I can't get any user input back from the program right now, right? It's running. On the system, but you can interrupt it with the keyboard, right? So if you do a Control C, that'll kill the running process, right? So the process disappears from top when you kill it with the Control C command here, right? So that's yeah, so that's how you can kill a foreground process. If you need to return control back to the terminal from the process that you're running, that's how you would do it, right? So you just hit Control C and you get you see here a keyboard interrupt. Now, if you're running simulations like this on your, say, this is supposed to simulate a sort of maybe a workstation in your lab, not on an HPC system, right? One of the convenient things you can do is actually push these processes into the background, right? And you can do that with the ampersand sign, right? And so if you just tack on the ampersand at the end of your command in the terminal, it'll return control to the terminal immediately, and it'll print out the process ID of the program that you're running, right? So this 28509, we go up to the top to look at the process table here. You'll notice something slightly different. This is actually 28510, and that just has to do with well, it has to do with running the time command as well with your Python process, right? So there's actually two processes here. You have the timer that's running, and you have the Python program that's running, right? So this is just the operating system ordering and tracking all the processes that are running on the system, right? So in this tutorial here, I have this fancy way to look at that process you can run. If I quit top here, we'll actually just look at that. Oop, it already ends. It already ended. Let's see. Okay, I have a, oh, I'm supposed to run it here. Sorry. Okay. Now, one thing that you, if you're managing process manual like this, is just like the foreground process, you might want to kill it, right? If it's running. And so the way to kill it is just to issue a command with the process ID. Right? You'll see here that it was terminated and the process disappears. Okay. So that's, one thing that, if you're, say, developing and running some code on your laptop or on a workstation in your lab, these are some of the commands that you might be using to sort of manage those processes while you're working on the system. The last two things in terms of managing processes manually is using the no-hup commands and the nice commands, right? So if you have a system like this that you're sharing with, say, researchers in your lab, or you're on some sort of shared workstation that you're using for your research, these two commands are what we used to use to sort of run code for long periods of time on these more powerful systems than just our laptops, but to do it in such a way where it wasn't really bothering anyone, or it wouldn't bother people if they were also doing sort of daily work on those systems, say, doing text editing or surfing the web. So these two commands, the first one is no-hup. What this does is it allows you to start the process and close the terminal. That's the key thing, right? So how do you set it and forget it, right? How do you tee up your calculation manually and run it on the system where you can just close the window, right? Right. If you did that with the foreground processes or just putting it in the background without this no-hup, closing that one terminal would terminate the calculation that was running, right? But you can see here in the second terminal, this process that I kicked off is still running, right? So that calculation is still happening. It'll still return a result. It'll just do so in this special output file called no-hup.out. Right? So there's no output yet because the process is still running. Okay, so I'm not sure we'll see if this makes it in the second. I'm not sure how useful this is. We'll see. Hopefully these I swear there's a point how this relates to batch jobs here in a second. Okay, so the last command here, if you're running on one of these shared systems, there is a concept of, as you can see here in top, of priority, right? You see these two columns here. This PR is for priority and NI is for niceness. This is essentially with top here, what we're looking at is how the operating system is scheduling these processes on the CPUs that are available, right? And these priority parameters, niceness parameters, have something to do with controlling which processes are getting more compute resources, memory resources at any given time on the system, right? And this is exactly what we're going to talk about here in a second with batch job scheduling, right? We need to control essentially what resources are being used on these HPC systems. So let me run this last example here, and we'll move over to the HPC side of things. Okay. So this nice command added to our set of nested commands here with nohup, nice, time, and Python 3. It allows you to control, again, which version of these commands will finish first, essentially, right? So if you have a high priority job, you will run it without the nice command, right? Because that'll run immediately and without sort of any restrictions or less restrictions from the operating system and the scheduler, essentially. So let's just start these three processes and just show you kind of what that looks like. We see here we have our three simulations estimating pi, but in this case, which we didn't really look at in detail before, but you see that the priority numbers and the niceness numbers are now different, right? You've controlled how much you weight the priority of finishing a given task, a given program, right? So this first one with where we did not use the niceness parameter, it sort of has the default of 0, and it's getting 100% of one of the CPUs. There's only 2 on this system, right? And so the other 2 are having to share the resources on the other CPU on this system, right? And so you can see that the operating system and the scheduler here have sort of divided the time in a certain way where almost 90, the second process here gets almost 90%, and this one gets about 10% of the CPU resources as all of these processes you're trying to finish, right? And so you see here the last one to finish is obviously the one with the lowest priority setting. And yeah, so that's just a quick demo of how this is done sort of manually. If you've never done this before, maybe definitely come back and maybe work through this section. This is the one that's kind of finished, mostly finished, at least in terms of I think all of the commands that I kind of want people to get familiar with in terms of doing this manually, right? Now, why did we walk through this? Well, you don't want to do this manually if you don't have to, right? So I remember doing this a lot in grad school until I got access to like a campus cluster that was running a batch job scheduler. And that's sort of what we're going to talk about here. But the concepts are very important, as you'll see here in a second, okay? Okay, I'm going to close that out. I don't know if are there any questions in the chat, Cindy? Maybe we should take a quick look.
Not at this time.
Okay.
Oh, never mind. Someone has one.
Okay.
Livia, did you want to? I'll let you unmute yourself to ask this question if you'd like to.
Okay, it's just a quick question. Like if you run a process in the foreground versus the background, the efficiency is the same, like it's going to take the same time, or is like more faster when it's a foreground process?
So in theory, right, you can change the priority, I'm pretty sure, of the foreground processes as well, right? So you could run, say, the nice command with a foreground process and change the priority that you've set on that process when you're doing it from the command line, right?
Okay.
So it's, yeah, this is more, what we used to do, when we just had, this is how we managed things on our workstations. We would, the rule was, unless you're actively working on some sort of debugging and the system's not being used, if you're going to do a long simulation, you set it at the lowest niceness, so it niceness 19, because that'll allow people who are maybe working on the system as well to
Okay.
interrupt your simulation and get it done and get their work done. But yeah, so I mean, I don't know if this, managing things, going through this sort of manual management process it was a useful exercise. We'll see. I'm sure people have some comments and suggestions for the future. But I think let's go ahead and move forward to the batch job part for the second half of the talk here.
Okay.
And hopefully it'll make sense of why understanding some of that manual process is important for how you interact on an HPC system, right? And so you have some nice idea of what's going on behind the scenes, right?
Okay. Thank
Okay.
you.
Yeah, let me see. Rebecca has one other question. So is the niceness just the inverse of priority and lowestness? Yes. So it's I think it's, Rebecca, I think it's just priority is equal to something minus niceness. Yeah. Yeah. So basically, if you look up in the documentation, you can have a priority or niceness somewhere between, I think the priority goes between 0 and 40, and the niceness can go from minus 20 to 20. Why those numbers exist, I don't know. I'm sure there's some historical tidbit that someone could dig up. But yeah, so it's all relative. So it's sort of, it's just 19. If you set niceness equal 19, that's the lowest priority. So, those processes will get interrupted for anything that's higher, right? The operating system will give more resources more quickly to the ones that have a different a lower niceness or a quote unquote higher priority, right? Yeah, if you haven't worked with these commands before, it might be a bit confusing. Nice thing is, if you're working on an HPC system, you won't have to, right? Okay, so that's what we're going to talk about next. Okay, so
I have a naive question, if I may.
Sure.
Yeah. So when you run this computation, so the duration of the computation and the resources used can be defined, or they are defined automatically?
So, very good question. As I did this on this first section, which is one of the reasons I kind of wanted to walk through it, is you don't really have necessarily an easy way to define those types of constraints on any program or process that you want to run, right? And that's the point of having one of these batch job schedulers, right? So, which is what we're going to talk about here, right? So so those exercises there that I ran, all those processes will just run until they're done, right? Or I interrupt them or kill them, right? Manually on that system that I was running, right? There's nothing that says like, oh, only run this for an hour. If it's not done, then kill it, right? You have to actually, come back and kill it if it's still running, or come up with some other way to, set that constraints, right? And that sort of leads very well into the HPC side of things, right? Okay, so let me, yeah, we have like 20 minutes left. I'm going too slow, I'm sorry. This is what we're coming to now. So this is sort of the mental model that you should have in mind when you start working on an HPC system, right? So how we were looking at in the first section, I was working here. I'm on my Zoom on my laptop at home giving this talk. I was logged into this workstation computer over here, running those estimates of pi on this workstation that was, in the cloud over here, and everything was being communicated over the public internet. Sort of looking at the outputs and things like that, right? And I was manually running those processes on this server over here. Now, when you come to an HPC system like we have at SDSC, right, these systems are a lot more complicated, right? So we have different types of computers all networked together, and they all do different things, right? And so the first ones that you interact with when you log into an HPC system is you have these login nodes, which we'll talk about, right? Behind the scenes, you have the compute nodes. That's where you want to run your processes, your calculations, right? So instead of just running directly on, say, the servers that you log into here, like I was logged into this server over here, you want to launch your processes on these compute nodes where you have a lot of the compute power on the system, right? There's other parts of the system that are tied together. You have management nodes that sort of help run the HPC system and all the software that you need to run the system. And you have storage nodes that run these sort of shared file systems, so that when you are running your code out here on the compute nodes, you have access to, say, disks that you can write to that are also mounted on these login nodes back here, right? That you can look at your data once the job is done, right? So there's a lot of different pieces, and again, there's a lot of terminology behind this, that if you're not familiar with, that goes into these things. But this is the cartoon view. This is more of sort of the detailed view, right? So this is a architecture diagram of Expanse that we have at SDSC, right? So all of these compute nodes are sort of organized into racks of computers, with each rack having a network switch. So each of these computers are connected to a switch in each of these racks, and then each of those racks are connected to a larger switch that connects all of the nodes together so they can communicate with each other. This is important if you're running large parallel jobs, right? We've only talked about running single processes so far, but you can run multiple processes across multiple nodes on these systems, right? If you have a sort of a parallel code that you want to run. And yeah, so again, there's lots of details here. I've got a link here to the Expanse homepage, which, if you're new to Expanse, there's a user guide here with all the information about the system. You can also see what, if you actually want to see what one of these systems looks like building, there's a link to the time lapse of the system being built. But again, in addition to having all these nodes networked together, there's connections to external networks and research networks across the US. So there's a lot going on here, right? But the thing that we're talking about here today, in the last bit here, is how do you get your processes running on this complicated set of hardware, right? And there's all sorts of different things that go into managing how these systems work, but the one that you're going to interact with the most is the batch job scheduler. And on Expanse, we run Slurm, right? And from this diagram, so there's a link to, I think, this Slurm homepage here, or no, to the Wikipedia page. You can read more about it, but you're going to interact with some of these background daemon processes that Slurm is running. Right. This essentially is an application that will control how your processes get run on all of this hardware that you have access to, right? Now you'll have a few set of commands that you'll be using to interact with this application and launching your processes on the clusters, right? And so Slurm is the most popular, I would say, batch job scheduler that's used on HPC systems. So if you learn how to work with Slurm on, say, Expanse, you'll probably be able to translate a lot of the knowledge that you learn running Slurm on Expanse to other systems as well, if this is your first time. Okay, so a lot of material here. Okay, so what I'm going to do now is get to our first batch job, right? Now, what you want to do is log into your HPC system. So the first thing I'm going to do is log into Expanse and take a look around, right? So just like I had that workstation computer where I was running my processes, I can run top on one of the login nodes, right? So you can see here, this is my username, and this is one of the login nodes on Expanse, right? And if you run top here, you'll see there's processes running, right? But what you'll see, instead of like on the workstation computer, it was just me and the root process or the root user, you have other people here, right? These are shared resources, so users who have access to Expanse are running simple processes on the login nodes, maybe compiling code. What we're going to do is, edit a text file and submit the jobs to the scheduler, right? So you can write your own, you can do some development work on the login nodes, you can compile code. But the key thing to keep in mind is you don't want to run your computational work on these login nodes, right? This is like the no rule. You don't do it, right? Okay, so so these are shared resources for all people. So yeah, I kind of wrote this down because while I was trying to finish some of this material this morning, there was someone running molecular dynamics code on one of the login nodes here that I had to kill. So there are some rules when you're working on an HPC system. Rule number one is you don't run on the login nodes, right? So you can do lightweight work like we're going to do now, like editing text files and submitting jobs and maybe transferring data, but they're not really meant for running your processes. Okay. This is clearly going too long. I'm sorry. Let's see. Okay. So what is a batch job? Okay. We're now 50 minutes in. That's probably not a good start. Good sign. Okay. Okay. So a batch job is how you're going to structure your request for resources from the Slurm scheduler on Expanse, right? Or any system that you're working with. Okay, so how Slurm manages things, you think about it like air traffic control, right? So you have jobs that are on the system, right? And you can look at the jobs that are running on the system with this SQ command, right? And so that lists all the jobs that are running out on the system right now, right? Now, if you look carefully at the output of SQ, you'll see that there's, just like the top command, right? There's different pieces of information and about each of these processes that are running. In this case, we're calling these processes batch jobs, right? There's a job ID, there's a location or a partition where they're running. So these how Slurm organizes the resources is into partitions. So you have different types of compute resources on the system. You have, say, in this case, a name for the job, the user that runs the job. There's a status, and let's fix this. A status of the job. So R is for running, PD is for pending. And you can see how long a job has been running on the system. And you can see if it's running, it's been assigned to a specific node or set of nodes in this case, right? You can view information about the nodes themselves on the system with this sinfo command. Again, it shows information about where this node is located on the system. And if it's up and available, nodes like jobs can have states. And there's a mix of things going on here of nodes that have been allocated to jobs, nodes that are idle and waiting for jobs. And so this is what Slurm is doing for you, right? It's managing your requests for running your job, which you will specify here in a second. And it's trying to assign your job on one of these nodes out on the system, right, to run your workload. Okay. Okay, so hopefully that makes sense. Okay. Now, what I wanted to get to here is to run our first batch job on Expanse, right? So if you do have access to Expanse, you can run this later. I'm going to run it here now. So again, just like in the first section, I'm going to clone my repository for my 4Pi repo to get the code that I want to run. And what we're going to do is write a batch job script, okay? And this is how you'll run your processes, your programs on an HPC system with Slurm, right? Okay, so this requires you to be, familiar with using a text editor. Hopefully you can, this is one of the sort of the prerequisites, hopefully, that if you're getting started on an HPC system. I use VI, is the text editor that I use. So I'm going to open up a new empty text file here. And how I usually label my batch job scripts is with just run, the name of the program, and maybe some additional information and .sh at the end. So .sh is just labeling it a shell script, right? And that's what a batch job it usually is, right? So you usually write it as a bash script, right? So this first line in the script that's shown here on the left is our first batch job script that we're going to submit, right? And this first line is just telling the system what type of script it is, right? And so you can name this, I mean, if it was a Python script that we were running, you could name it Python or Python 3, but I'm just going to run it as a bash script. Okay, so this is called the shebang line. But how you communicate with the scheduler, what you want in terms of, so let me back up here. So what's going to happen is after we submit this script to the scheduler, it's going to process this text file, right? And this text file has to contain certain bits of information to tell the scheduler, in this case, the name of the job, how you want to, where you want the job to run on the system, how many CPUs you want, how much memory it needs, and how long it's going to run, right? And so this is where you define your resources that's required to run the job, right? And give it the other metadata that you want to give the scheduler about your job, right? So these directives here are the directives that are used for communicating with Slurm, okay? So you have this first one, these are the minimum ones that I always put in any of my batch jobs. So you have the job name. So my first 4Pi test. You have to charge your job to a certain accounts. In my case, it's going to be use 300. This next line is to use a certain partition. And again, a partition is a type of, and basically Slurm organizes all of the resources on the system into different partitions, right? So we have this one partition called debug, which has 2 nodes available for you to run quick jobs that you're just playing around with, essentially, for testing things. You always usually want to request the number of nodes. In this case, we're running a very simple job, so we only need access to at most 1 node on the system. This next line is n tasks per node. So in Slurm terminology, if you look at some of the documentation, essentially what you usually think about is tasks are processes, right? So if you're just we're running a 1 process code here, right? So it's just a serial code. Think about task as process, or is effectively how it's to be sort of thought about here. And you want to assign how many CPUs do you need per task, right? You can have tasks with multiple, that do require multiple CPUs. In this case, we do not have one. We don't need a lot of memory here. So I'm just going to put 1 GB of memory. On Expanse, the default that you get per CPU is about 2. And then you have to make a request of how long, you need to tell the scheduler how long the job should run for. Okay. Now I'm just going to go up here with my python.py and some number of samples. Okay. So this is a basic batch job script, right? And this is the simplest structure that you can sort of have, right? So you want to give your job a name, you need to give an account that you're going to run it against, because we keep track of how much time you're using. You want to make a request of how many CPUs you need, how much memory you need on those nodes, and how long you think you need to run the job, right? Now, someone asked the question earlier, it's like, is there a way to constrain how long, these programs run? Yes, in this case, this is what, why, one of the things that Slurm does for you. If this code runs for more than 5 minutes, the scheduler will kill the job, right, and stop it there. Okay. Ooh. All right, running quite long. Okay, so this is my first batch job script, and it's going to probably end the talk here. And I'll stick around for anybody who wants to stick around longer, but I know some people probably have to go. But just make a few more comments here when I run.
Sorry, how did you escape the VI? Sorry, I never used this.
Yeah, so I basically VI, to get out of VI, what I did is I did a colon and a WQ, so it's just write the file and quit. So yeah, this is kind of one of the prerequisites probably for this talk in the future. Is you need to kind of have some text editing ability. But yeah, we can talk about that in a second here. Okay. So once you have your batch job written, right, you need to run it, right? How do I tell the scheduler, hey, this is my job, I want you to run it? In Slurm, that's this sbatch command. So you do sbatch run, and you submit the job, right? So you can kind of think about sbatch as a fancier version of NoHub, right? You've now launched this job into the scheduler, right? With all the other jobs that are competing for resources. It's giving you an ID, just like NoHub gave you an ID for the process you were running on your workstation. and you can walk away and your job will run and you'll eventually get output, right? And that's the whole idea of, using a batch job scheduler, that you will compose your workload and the commands you want to run on the HPC system. You make, these are the commands here. So you write the script, you tell the scheduler what it needs to give you to run your commands, and then you run your commands, your programs below that section of the batch job script. And that's your first job, batch job, right? So I know I went way too long and I need to sort this out a bit more. So I'm sure there's plenty of questions for people who are very new to this. So I'll definitely stick around and keep chatting with you all, but definitely, if you have any questions, feel free to email me. I can give you some more resources. Again, there'll be some more links to other material here on the tutorial eventually. If you go to the original page, there's actually a similar talk given by Mary Thomas, who was here earlier at one of our institutes here, where you have another video that probably does a better job explaining what the batch scheduler is and writing batch job scripts. But if people want to stick around, I'll definitely answer some questions. I think that we didn't get to any more of the advanced stuff that I was hoping to get to eventually. But yeah, I'll stop there and since it's at noon, and take questions here.
Marty, so if you want to start off with questions, there is one from Tongshi.
Okay.
It says, do accounts have priority on running jobs? Can we set jobs on an account always prioritized another account?
So yes, this is a good question. Okay. This is okay. Tom. Yeah, Tom. Okay. Yeah, this is. Let me go back to. Yeah. Do accounts have priority on running jobs? Can we set jobs of an account always prioritizing an account? So this is a very good question. So this is kind of one of the analogies of why we talked about the manual processes and setting priorities. So Slurm does set priorities for your jobs after submission, right? The whole reason for having the scheduler is to prioritize, figure out what your job requires to run, where resources are available on the system, and then when it should run, right? So there is something in Slurm called Slurm job priority, which is very similar to the priority and niceness of running your processes manually, right? So the thing is that you don't have control over that, right? You will be subject to what we call fair share scheduling, right? So how most HPC system operate is with a fair share scheduling model, which basically means that every job you submit will be assigned a priority, but that priority of the job changes over time, right? Where when you first submit your job, it'll be assigned a priority by the scheduler once it sort of gets into the system, right? And as resources become available, or how long your job is waiting in the system to run, your priority will get higher and higher as it waits, right? And as there's other factors that can change your priority over time, like how many jobs you have run recently is kind of will affect your priority. There's a whole slew of things that will affect the priority of the job. But the important thing is you can't set it, right? One thing you can do, which is one of the tips that I was going to try to give, is you do have some control though over your resource requests, right? So when you're writing your batch job, right? If I were to, set the maximum here. Oops. Sorry, if I were to set the maximum wall time I'm allowed here in this debug partition, right, to 48 hours, right? Say I want 48 hours, I want one core on this debug partition. What the scheduler is going to try to do is find me a block of time for 48 hours to run this code, even though we know it's only going to take a couple of minutes, right? And so the fact that I've requested more resources than I need is going to make my job wait in the queue longer to run on the system, right? And so anytime that you can write in your batch job, make a resource request that is more reasonable to what you actually need, you're going to get much more optimal sort of turnaround on your work, right? So in this case, right, running for 48 hours, I don't need that, right? For this simple job, I need like at most like 5 minutes, right? And so that job with the 5-minute setting will get through the queue much faster than one if it was set at 48 hours, right? So that's how you can sort of, work within the priority system and the resource scheduling environment of a batch job scheduler like Slurm. That's the first question. Okay, scroll back up here. So hopefully that answers that question. But I missed it. Where'd it go?
And next would be Amon, Marty. Will end
Okay.
tasks per node.
And CPU's task multiply to provide the total number of processors in jobs. Yes. So that's the idea. So again, so yeah, how you set these is a little bit more advanced for different types of jobs, right? For this case, we're really this was our first batch job. It's a serial job. We only need one core, but yes, if you need multiple CPUs, here, say if I needed to run, if this was a multi-threaded code, and I could use all 4 cores on a processor, the multiplication of this n tasks per node times the CPUs per task would give me 4 CPU cores when the job runs. So the scheduler will try to find me 4 CPU cores, still only give me 1 gigabyte of memory here for 5 minutes, and it'll run. In this case, this code isn't written for being parallel, so it won't really use those resources. So again, this comes back to, I guess one myth that people have is sometimes if you take your code to an HPC system and say, tweak some of these directive settings, here I'm asking for 4 cores. It doesn't mean the code is going to run and use all 4 cores, right? You have to write your code to take advantage of all of those cores at the same time. But yes, your question is yes. The multiplication of those two will tell you how many total cores are assigned. The scheduler will give you to use. Okay. So Siri, what is the difference between writing the shebang with the environment? Yeah. Okay. So yeah. There isn't a difference in this case. The more generic way for writing this shebang line is with this environment, because you can specify other types of environments, right? So like I said here, this could be Python, and then you could actually, I think Slurm understands Python. You can just run Python commands here, like imports NumPy or something like that, and calculate something. So you can do different things with this user bin environment shebang, but it's just a preference, I guess, if you're just running a batch job script with batch. So it's kind of up to you. But yeah, you can, again, Google's your friend. You can definitely read more about sort of the choice there. How do you determine how much CPU and time you need for your job, Rosanna? That's experimentation. If you bring your code to an HPC system, every HPC system is going to be slightly different, right? And so in cases like Expanse, we have these debug nodes where you can run test jobs, you can, get a feel for, how long a code will run for a given amount of resources that you've requested, right? So if it's a parallel code, requesting, 4 CPU cores on, the types of processors we have on Expanse will give you one sort of runtime and how much memory is required for a given calculation. It's really, you have to sort that out yourself. It's what we call sort of benchmarking your code. And we do have the nice talks. I think maybe Bob, Bob Sinkovitz is in the chat. He has a nice talk about parallel computing concepts and talks about some of this benchmarking your code and how to think about sort of how these different parallel codes fit on HPC systems and sort of how to present benchmarking results, because on these systems you usually have to apply for time for your research project, right? So you do need to sort of at some point understand how much CPU and memory and time you need for the simulations that you want to run on these systems, right? These systems are always in demand. People are always asking for time to run their science and computing needs. And so that's sort of, part of your task as a researcher running your own code on the system. Okay, Jacobus. Once you submit a job, like your example, where is the output? That's a good question. So let's look at the output. Let me undo some of these changes I made. Okay, that's a good question. Because I had some more sort of tips or exercises that will eventually be in this tutorial, but the output you can see here in the batch job script, right? I have this output line, right? And this is a little typo here. So correct this. Is kind of got a funny structure here compared to the other lines in the system, or in the Slurm SBatch directives here. And what this means, you can see I have these little sigils. So there's like a %x, a %j, and a %n. Now this is a special structure to this output line that Slurm allows you to use these special sort of variables. This %x, if you look it up in the SBatch documentation, is basically just repeat the name of the job. So it puts the job here. I put an O for output. That's just what I use. The %j will actually print out the job ID. And then this %n will print out the node, the name of the node it ran on, right? The host name of the node that it actually ran on. This is how I like to structure my output files. You can split these across multiple files. I just like them all in one. But what we should see, if my job here, 207597889 ran, we should see the output file. By default, it'll be dumped directly into the working directory where your job was submitted, right? So we should see, if I do an ls here, a output. It looks like I had a typo. Let me resubmit the job here while we wait. Live demos is always hard. Okay. So if you are working on the scheduler, usually you only care about the jobs that you're running. I have some other jobs that are running here. So you can see that my job that I submitted here is already not in the scheduler. So we should have an output. And you can see here, that's the output file that I mentioned, that the structure it would be, right? It would be the name of the output, or name of the job ID, and the job, and the node that the job ran on, right? So if I look at this, I can look at the output. And there's an error here, but we don't need to. We can talk about that if people want to stick around. So that's but by default, when you write your batch job scripts, right, the output, there's always going to be an output file where the standard output from your program is going to be written. How you specify that with Slurm is with this output line, and you just have to give it a name. I could have just named it, this is my output as well, right? And that output file is just going to be written to the directory where you submitted the job, right? You can always change that, but it's usually mostly convenient. What I do is I always put the run script in a working directory, because sometimes you'll have input data, you want the output data to be in the same directory. You can change the directories and do all sorts of things, right? This is just a batch script. This is just a shell script, right? So you can run any sorts of commands you want here, right? You can change directories to, here we have scratch disks on, I won't go down this route right now. Let me go back to the questions. But yeah, so that's where your output file is. By default, the output file is always in the working directory where you launched the job. Okay, let's see. Okay. Each top S account is also good for this. Yes, so Mark Piercy mentioned HTOP. It's a fancier version of top that you can use. S accounts is a good command that you should get familiar with Slurm. It allows you to look up information about running and completed jobs, right? So the SQ command is really just for running jobs or jobs that are either running or waiting to run. S account allows you to look up jobs or look up information about jobs you may have already run. Can you break down the output commands? Oh, I did. I think I already answered that one. I assume this was the question. Okay, Victoria, do you have any resources on automating Slurm job submission? I have 48 jobs that I want to submit on a partition. It has a maximum of 24 hours, I'm guessing. Maximum of 24 jobs, maybe. Is there a way to schedule it so that way when one of the first 24 jobs finishes, I'm going to submit the job next? So this is a good question. So one thing that I didn't get to, which is important, I'll just go to the Expanse user guide. So whenever you're, writing your first job scripts for any HPC system, you really want to go to the user guide. So what Victoria is talking about here is the different partitions. These compute resources are available on the HPC system. Again, they're broken up into different partitions, but each partition usually has limits. So what she's mentioning is that, even on Expanse, we have certain limits for the different compute resources, right? So for example, on this compute partition, which gives you access to these one type of nodes, you can only have a maximum of either 32 jobs and or 32 nodes in a given job, right? So there's limits on the amount of jobs you can submit to these partitions, and there's also limits on how much resources you can request, right? So you can't say request, let's see. Oh, no. So here I can't say in the debug partition, request 4 nodes. I want, all 128 cores that are available on each of those nodes. One, because in this case, there's only 2 debug nodes on Expanse. So this is just a job that you can't even submit, right? You'll get stuff like this. You'll get errors when you're trying to communicate with the scheduler, like I want this. It's going to say no. There's going to be limits to what you can submit. What she's mentioning here is a little bit more complicated, right? Especially when you have a limit on the max number of jobs that you can submit, right? So for example, in this case, in the compute partition, we have a max of 64 jobs. So there are, Victoria, it really depends. Yeah, there are ways to do this, but there's not an easy way. There's essentially workload managers that are you can use that will sort of manage your job's submission from like another host, right? So for example, if you were to, if I had, if you have say your workstation computer, your lab or desktop at home, you could set up one of these sort of workload managers that would allow you to submit the jobs to that local workload manager, which knows then how to submit jobs to an HPC system, right? And it might know that, and you would have to set up that that the limits are this, are a maximum of 24 jobs in this partition, and it would regularly check the HPC system to see, oh, am I below my 24 limit? Okay, submit the next job, right? So it gets complicated. If I can send you some material if you're interested in some of the ones that people do use. Yeah, it's a long rabbit hole of ways to do this. I'm hoping at some point we'll have an easy way to do this on the systems at SDSC, but we don't right now.
So
yes.
Yes, in a nutshell, like what is the difference between interactive as opposed to batch?
Yeah, so again, a batch job is kind of like the background process, right? Where you set up the job, you request the resources, you run the process. I mean, you submit the job to the scheduler. The scheduler will just figure out where it's going to run, when it's available when it's going to run, in competition with the rest of the jobs on the system. An interactive job is a little different in the sense it's more like the foreground process, right? For example, if I want to run an interactive job on Expanse, we have a little line here of an example in the documentation here, and you use this srun command, and I'll show you what that looks like here. And you'll see that it's much more like the original sort of running the process on the terminal, running your program on the terminal, essentially, right? So if I want to request, again, some resources in the, like if I just want to request again, sort of one CPU core in the debug partition for, let's see, mem equals 1 GB we had, time we had for 5 minutes, but here I'll just set it for 30. So there's, again, you'll notice that these command lines here correspond, a lot of them, to the same sbatch directives that we had in your batch job scripts, right? So again, this srun command is, what you would use to set up an interactive job, what we call an interactive job. And what it's doing is it's, again, requesting resources from the scheduler, just like the sbatch command is going to do for your batch job script. But again, what you see here is I have access to this Expanse 955 node, right? So it really opened up a new shell terminal on that node for me with the requested resources, right? So in this case, you could go to the 4Pi program again in this repo and run the application, right? And now you have, just like you had before, you have a foreground process. You can set it to the background, right? So that's what we mean by interactive. Like you're, again, interacting in the terminal, essentially on the command line with the application. When we talk about interactive, you might also be talking about like a GUI based program that you might be using. We have some visualization applications that will run with a full GUI on the system, so that would be an interactive application as well. But the basic idea of an interactive is this. where you have
Yeah.
access directly, just like I did on that cloud node that I was doing the first examples on. It's kind of the same thing. It's like you want some time on
Okay.
this resource, it'll figure out where to put your request for having access to those resources. But the thing you have to remember is it's not going to improve your sort of wait time, right? So if you need to do some interactive work like this on one of the nodes in an HPC resources, that request for an interactive session is typically going to wait as long as it would for a batch job of the same request, right?
Okay.
Unless they've set it up that way, unless they have, you know, some HPC systems have, say, an interactive partition or queue, right, that are sort of dedicated for this type of work, right? You can kind of think about this debug partition as an interactive, kind of an interactive queue, right? We've really set it up so you can get as much as possible a dedicated resources for doing debugging work, right? You know, because we've limited the jobs here to only 30 minutes. It's, you know, hopefully, you know, not too many people are using it all the time to do actual, you know, heavy computational work. It's really for, you know, doing quick interactive iterations of, you know, maybe, you know, debugging your code that you're going to run on the full system, or, you know, simple exercises like this, you know, that you might want to play around with. So hopefully that makes sense.
It makes perfect sense. Thank you so much. So that means if, let's say, okay, so I run an interactive session and then I create some virtual environment, for example, Python, and I want to launch some, like, let's say, Jupyter notebook. So I will be able to do so from the terminal.
Yes and no. So I say yes and no because you mentioned the keyword Jupyter notebook, which you know, is always a hot topic of conversation, right? And was this morning as well. Yeah, Jupyter notebook is a perfect example of what we would call like an interactive application, right? That many people obviously want to run, right? You're going to want to, yeah. So, you know, we'll talk about Jupyter specifically because I'm sure many people are familiar with it and interested in running those on HPC systems like Expanse. The best thing to do is to if you're going to run a Jupyter notebook, right? One thing you have to remember is it's you're actually running like a web server, right? And that, you know, web servers are targets of attack on the internet, and you have to connect to that web server somehow over the internet. And there's ways to run Jupyter notebooks on HPC systems or just remote systems in general in a secure way. You know, if you're, you know, working on another HPC system, say not at SDSC, I would reach out to your say your staff who run that system that you're working on. If it's like a local campus cluster or another HPC center, you know, send them an email through their ticketing system or whatever they have to ask them how they would like you to run a Jupyter notebook or something like that, or a web service like that on the system. Because there are other things people run, like things like Shiny apps, which is like an R web server kind of application environment as well. But if you're talking about SDSC, we have a specific helper script essentially that helps you launch Jupyter notebooks.
Okay.
And I can give you that here. So this is the documentation, which I'll post it here. But essentially what it does for you, and I'll run a quick example here, is it eliminates a lot of the, what it does essentially is it'll kind of like the interactive command that I just ran. Essentially, you know, takes an input that, you know, how much of like how many CPU. Oh, sorry. Let me know what the command looks like here. This is just a quick. a quick version of it. It's very much like that srun command I ran. It's like it's a command line tool that'll launch the Jupyter notebook for you. You just need to say provide an account name, what partition you want to run in, how many CPUs you want, how much memory in terms of gigabytes you want, and then you have to give it sort of some specification of how to set up your Jupyter environment. It sort of assumes you have Jupyter installed. This is one sort of software environment that has Jupyter pre-installed, so it just runs. And what it does is it'll output what it does under the hood is it writes a batch job script for you, submits it to the scheduler, and all you need to do is copy and paste this application or this URL into your web browser.
Okay.
Okay. So if you're doing it on an SDSC system, we have this special helper script that does it for you. But if you're running a Jupyter notebook on another system, they might have a particular way they want you to do it. They might have a Jupyter hub set up for you to run your Jupyter notebooks as well.
Okay, understood. Yeah. Thank you so much. That makes perfect sense. Thank you.
Yeah, no worries. Okay. What was the other commands here? Clean up mine. Let's get back to our material here. Okay. All right, questions. Where to go? We have Bob's computing. Where did we leave that? Breakdown, we answered those.
I think we're at Shenglin.
Yeah, Shenglin.
Yeah.
If my job will use the specific tools I installed in the specific environment activated in my login nodes, can the compute nodes automatically call the tools and options correctly? Okay. Yeah. So this is, yeah. So I mean, this is a complicated question. Managing software environments. Okay. So, but it's a good one. Let's do it in the context. Let me answer that in the context of kind of the batch job examples. Okay. So let me go back to, let me increase this a little bit. It's too large. Okay. Okay. So let me go back to my batch job script here. All right. So this is our batch job. I'm going to submit it. Let's go back to our original configuration. I just want one CPU. Submit the job. Okay. And this is the output. Let's just look at the output. Fix that typo in a second. Okay. So this comes to Shinlin's question. So even though I wrote this batch job script, I requested the resources I want, you can kind of see what the output was. The output was, I can't find this program that you want to run. And this comes to the issue of, even though it found Python 3, right, is available, right? Python 3 is available on the login node. And will it be this version will be available on the compute nodes as well in the system. This is the base Python version that's available on all the nodes that comes with the operating system that we install on the system. So we have a version of Python that we can use, but it can't find the application that I actually want, or the Python code that I wanted to run, right? And so the reason for that is when you're writing, all this is a shell script, right? You have to tell the operating system how to find your code, right? And that's one of these sort of base skills that is important to learn, is how to modify your path environment, right? So this path variable is an environment variable that tells the operating system essentially to, where to look for executable code, right? So I can, for example, print out the path variable. I can print out the path variable that's in my environment right now on the login node, right? So you see all these paths to different parts of the file system that's both on the login node. There's some file systems that are not on the login node, but on other parts of our storage system. And this, for example, this seam shared file system here. Again, you saw me modify this path variable to get access to the Galileo scripts that I ran. So this path is where your, what we call, is part of your environment, right? That controls how commands are executed in your terminal or in your batch job scripts, or in your scripts that you run on the system, right? And so if I want to find, if I want to include my application that I want to run here, I need to modify my environment here, in this case with the path variable, so it knows where to find my py.py application or code that's being run, right? And so this is what we would call an environment modification, right? So I'm modifying the environment to put my executable in the path of the environment that the job is creating, right? So one of the next most important things about writing batch job scripts is not only making a request for what resources you need and all the metadata that we've told the scheduler about our job. In addition to the actual command you want to run, you have to set up the software environment that allows you to run that command. That's what Xingling's question is really about. Like, how do I get my batch job to set up the correct software environment to run the code? Well, you have to write that into the batch job script, right? You have to tell the scheduler, hey, these are the commands that set up the environment. And then these are the commands I want to run in that environment. So the next step sort of layering your job script is, setting up the software environment like we've done here. So let me go ahead and see if I can run this example real quick. Run too fast. Let's see. Hope I didn't make another typo. I can't find it. Where is it? Did I delete it? Did I? No. Let's see here. Should be right. Something's not working. Okay. Let me make another example here then. Let me just do it on the command line to make sure I get this right. Might be some subtlety here that I'm missing. Okay. Yeah, there's some subtlety here that I'm missing here because because I issued the Python 3 command, it's not looking at this py.py as an executable. So, but if I did something like this, it should be fine. Basically, here it's requiring me to point explicitly to the script in this case. Okay. Anyway, so hopefully that kind of answers your question. There are other things when you're first getting started with, the other big thing to, setting up your environment on an HPC system is we have what are called software modules, right? So we have default software that's available on the system itself. So for example, you can load different compilers on the system. Those by loading that module allows you to access other pieces of software that were compiled with that compiler. For example, I can also load a new version of Python. It's not the same as the one that I just ran using the operating system version of Python, right? So you can modify your environment, your software environment with these module load commands, right? With this pre-installed software we have. And that's the same thing you would do in your batch JavaScript. So if I did a module load GCC 10.2 module load Python 3.8.5, this is another way that I would modify my batch JavaScript here to get a new software environment to run the same code, right? Now, this is a pretty simple change. Moving from one version of Python to the next, there's not going to be a big difference in how you execute it. But depending on what code that you're trying to run or the code that you're compiling, anytime that you want to run code that you compiled with some of these software modules, you need to make sure you put those same software modules in your batch JavaScripts, right? Because you need to recreate that same software environment that you use to, say, compile a piece of code when you actually want to run it out on the system, right? And so, building in how you set up your software environment, is an important part of writing your batch JavaScripts as well, right? You need to replicate the environment that the code should run in the batch JavaScript as well.
So do you mind sharing a link to any existing documentation you have on your website?
Sure. Yeah. I mean, so there's examples, I think in the, you'll see some more batch JavaScript examples here in the expanse documentation.
Okay. Thank you.
Where
so
you
much.
see here, you're loading different pieces of code that, there's also examples that are available on Expanse if you have access to Expanse. But yeah, if you don't have access to Expanse, some examples are available here.
I think if I have access to Access, then I can, by extension, have access to Expanse, correct?
Yes, if you've been allocated time on Expanse. If you haven't, you can always request through Access.
Okay.
To move your credits. I think they call them credits now around.
Okay. Thank you.
Okay. Let me see. Thinking. Okay. Let's see. List of shilling. Can we build compile software on login nodes? Gabriel, if you're still here, yes. However, it depends. I recommend you actually write if you're compiling code from source. I recommend actually writing your own batch JavaScripts to compile the software. This solves a couple problems, right? As we just discussed, when you want to go run that code that you've compiled, you need to recreate that software environment in a script anyway. So you're going to have to write that script down. You have to write down that software environment by, say, the different modules you've loaded, or say the Conda environment that you've activated, you're going to have to write down the commands that you've issued to create that software environment that your code was compiled in, right? And so if you do that at the compilation step when you're building the software, then you just take that and start modifying that version to when you actually want to run the software, right? So hopefully that makes sense. If you have problems compiling your software, or you're changing the different modules you might be using to compile the software, having that output from the compilation process itself is helpful as well, right? Instead of dumping all the output to the screen or to manually to a file, you just have, the output file from the batch job that is used to compile the software. You have all the output from, say, the make commands and any other things, configure commands, like whatever you ran to compile that software is going to be contained within that one instance of the build job that you ran, and it'll help you debug things, I think, a lot better long term. That's what I do typically. But yes, you can use the login nodes for compiling codes, but structuring them as batch jobs is also quite helpful. And in some cases, on Expanse, for example, right, we have two primary types of nodes. We have compute nodes, which are only CPU based on AMD processors, and we have GPU nodes where we have Intel CPUs in those GPU nodes with NVIDIA GPUs, right? So we actually have not only two types of main compute resources, the AMD compute nodes with AMD processors, we have the GPU nodes, but those have Intel processors. So if you compile something for the GPU codes on the login node, depending, if you're not careful, right, it's going to think that it's going to run, the code's supposed to run on an AMD processor, not an Intel processor, and you can get into some weird issues. So in our case, we always recommend that you actually compile your codes on for GPU codes, we actually recommend you compile directly on the GPU node, so you don't get this sort of confusion by compiling it on the login nodes. In some cases, it's almost impossible to then compile on the login nodes anyway, but it's just better to compile on the hardware that you're actually running on. It makes things a lot easier. So let's see. I need to specify my data folder in the batch commands. I'm not sure, MD, what that's referring to. But yes, if for example you have a code that you're running that requires some input data, and it's not in the working, the input data is not in the working directory that you launched the job script from, you do need to specify the paths and things to where to find that data, right? Just like I had to specify where to find my pi.py code here. If you have an input file that you need somewhere that's on the system, you also have to probably point to that for your application to run correctly, right? So yeah, it depends. If it's in the same working directory where you launch the script will be able to find it pretty easy. If it's somewhere else on the system on a different storage resource, you'll need to point to where that's at. And again, all the scheduler is going to do for you is, give you the compute resources you requested, and it'll execute the commands here that you've written. If executing those commands wouldn't work interactively, they're not going to work in a batch job script, right? So you have to just model the same thing you would run manually, on a workstation in the batch job, essentially, right? Everything that you would have to do to make the code run correctly manually, you have to make it, write it down in your batch job script for the scheduler to run your workload correctly. So it's hopefully that makes sense. Let's see. Thanks, Trevor, for helping answer questions. Jacobus would love to see this as a 2 or 3 part series. Yeah, I know there's too much to cover here. I'm working through it. I will definitely eventually have a tutorial together and break this up in a better way. Hopefully you found some of it useful though. Let's see. MD says, I need to run cryo jumps, which is not which I was used to Railway GUI, but Expanse does not have the GUI. Do you have some suggestions? That's a very specific question. MD is asking about a specific application that we have on Expanse called Railway. I don't know enough about the GUI from Railway. I know that we, don't compile Railway with the GUI. We can probably look into that if you want to send us a ticket about getting that set up. We can definitely look into it. I don't know if there's a reason why we don't typically have the GUI incorporated. Running GUI based applications on HPC systems is always kind of a pain, as you saw with just Jupyter Notebook, which doesn't necessarily have a GUI per se, but it runs a web server. These types of applications take a bit more time, bit more work to get set up correctly and safely. And so that's, definitely if you're interested in the Railway GUI, just send us an email through our ticketing system. I think it's consult@sdsc.eu if you want to follow up. Let's see. Chase, do you use LMOD or a module to manage software environments and associated environment owners? Yes, Chase, if you're still here. I kind of touched on that here in the last couple of questions, but setting up software environments is kind of a whole nother talk, which we do have, or we should have one dedicated for that. Yes, obviously you can, LMOD is this, is for those who are still here and aren't aware, that's what sort of we use. It's the software that allows us to set up this module environment where you have these module load commands that then what it's doing under the hood is modifying your environment variables so it knows where to find this compiler and this version of Python that's been installed on the system, and makes your process of modifying your environment much easier to access this software, right? So that's what Chase is asking about here. Adrena, do SBatch files vary based on different modules? I think the answer to that question is yes. I think you're asking is, well, maybe, how do we make those changes on the SBatch files, for example, Gaussian? Okay, so she's asking about a specific question. Or specific sort of examples. So if you're on Expanse, we have and this is, I think, at the end of, I have this link somewhere in the, or this document somewhere in the tutorial, but it's not quite obvious. We have some examples here. She's asking about Gaussian is an application that we have. So you can find example, let's look at a GPU one. Example batch job scripts for different applications that a lot of people use and are pretty popular, but might be again a new user to an HPC system and not familiar with all the how to set up the batch job script for that specific application. So we have some examples here with input files and things that you can use. And so she's asking about the Gaussian one, and so I'm not sure exactly how do we make changes. So I mean, again, these are just text files, right? So you can make, so if I wanted to copy an example to my home directory, I would just copy the Gaussian GPU examples here to my home directory, and I would have access to that example batch job script, and I could start modifying it. Like, right, I don't like the bin bash version. I'm just gonna be, pedantic and change it to the way I like to see this written. I don't like using quotes. You don't really need the quotes. Not too important. I like my output to be structured like this. Right, so again, these are just text files, right? So you can modify the examples that we have for any of the applications that you might be using. that we have examples for in that directory as needed, right? The Gaussian one's particularly a little weird because of that CPU sets thing that has to run with. Anyway, we don't need to go down that rabbit hole, but yeah, so again, a batch job file is just a text file that's written usually as a bash script. All it's doing is communicating to the scheduler what types of resources you want, and the rest is just commands that you could run. You can run all these commands essentially, on the command line and run them in an interactive session. It's just inconvenient to do so, right? You might be waiting for that interactive session to start. You just want to, set up the job and forget about it and come back when the job's done, right? That's what you need to, sort of do to learn why you need to learn how to write, batch job scripts. Okay.
So Marty,
yes.
Yeah, so typically a user and a no-root user have a limited allocation, right, in terms of storage.
Yes.
And so let's say you have some big data and then you have big outputs as well. So, and you are on a computing node it's up to me to define where the output should be exported, or it go automatically to specific, storage allocation of mine. Or can you speak to that, please?
Yeah. Let me just. It's a good question, right? I mean, this is what we need to eventually get to in kind of this tutorial. Is all right. So, the first part of working with batch job scripts, right? Obviously, we talked about you have to tell the scheduler what type of compute resources you want, right? And those compute resources are sort of just individual computer nodes out on the system. They have, some number of CPU cores. They have some amount of memory. They might have GPUs. On Expanse, and in a lot of systems these days, they have like physical sort of storage, local storage on each node, right? So there are, essentially a hard drive on each node that you can use while your job is running. We call this the local scratch on Expanse. So if I go to the storage section of the Expanse user guide, it talks about the different storage systems we have. We have or different file systems where you can store things. So we have the local scratch disk. This is what I'm talking about. On every time you launch a job, whether it's interactive or batch, a directory gets created on that node that you're running on, or the set of nodes you might have. And you have access to that shared local scratch disk, right? So this is where you can put temporary files or anything that has a lot of high I/O requirements, right? So if you're writing a lot of small files, this is where you would want it. These other file systems and storage you have are what we call shared or network file systems, right? Like, for example, my home directory here, right, is not physically associated with storage devices that are on the login node, right? These are sitting on another server across the network here within the HPC system, right? And so in this case, right, when I'm running my batch job script from my home directory, right, we saw that the output file is written directly to my home, right? So let me just rerun this again. Right. So when I submit my job, that batch job script is going to go out, run on one of these debug nodes, write that output file back to my home directory, because that's sort of the default behavior of the batch job script, right? But that's storage for your home directory, right? What happened is, right, that batch job was submitted to the scheduler, which is running some processes on the management node. It said, okay, take that script, put it over here on this compute node here, run it on a CPU that's available on that node. And then the output was written to a storage device over here, and you can then see it mounted on the login node when it comes out, right?
I see.
Right, so there's a lot going on behind the scenes. And similarly, we have these other file systems like the Lustre file system, right, which is also another networked file system. So if you need to use Lustre, which is good for large parallel I/O is what it's designed for, and where no, I think it's still running. Okay, the job's still running. That's why there's no output. So yeah, so you do need to control where your input and output is coming from in your batch job script is the short end of it. For example, if I were to do something like this, if I were to go to if I were to do something like this before my job in my job script, which is using some more environment variables, what it's doing is, right, I'm changing directory to that local scratch disk on the compute node itself. So the output from this standard output, well, I could redirect it to a file, a temporary file on that actual node, right?
Yeah.
And so it'll write that file, that temp file, for the batch job script here if I submit it.
Yeah.
So I can show you kind of how that works, right? So you do have full control over where things are going, right? This is. Which one is this? 341, right? So you see that temp.out file is there.
Right.
It was created by me redirecting some output to that local scratch disk. But the thing about this scratch disk, right, this storage device, the resource that you have access to, it's temporary, right? It's going to be deleted at the end of the job. So if you were to need to use like the local scratch disk, you would then need to copy that temp.out file back to your home directory, essentially.
Yeah.
At the end, right?
Yes.
So things can quickly get complicated, right?
Right.
Depending on what you're doing.
Right. And so,
but yeah, again, the thing to keep in. Oh, I have too many jobs. I think there here, right? I have too many jobs already in the debug queue. That's why this is first on. But anyway, so yeah, hopefully that answers your question.
Yes, you did. Thank you so much. That was very, very helpful.
All right, I think that's all of the questions. Is anybody else who's still sticking around? Okay.